Yeah, comes on everyone. Let's start off. The last thing that we did was the sphere problem. Before going ahead, let's do one more. Let's say this is M. No slipping. This is mass M, radius R, solid cylinder. So we have a string here which is wrapped around it. Find the acceleration of the block. This is a smooth pulley, so there is no friction on this pulley. Let's get this. Others do keep your cams on. Let's go ahead. One more minute. Let's see. Remember the process. The steps are still the same. Step one, choose your system. I will take the solid cylinder and the block. So draw the FBD. tension, mg, normal reaction, friction. This will be the same tension T, and this will be mg. Let this go with A, and let this go with alpha. So that means this topmost point here, and this is the acceleration of the block. We know this point is going with A plus R alpha. This point is going with A minus R alpha. Because it is in contact with the floor, this must be equal to A ground, which is 0. So A minus R alpha is equal to 0, A is equal to R alpha. I could actually kept a plank at the bottom, and A will not be equal to R alpha. And this thing here is the acceleration of the block. So along the string, the acceleration must be same. So acceleration of the block must be A plus R alpha. And we know A is equal to R alpha, so this must be 2A. So the block is going with twice the acceleration of the cylinder. Is that clear, everyone? Then you're done. Write the force equations. Again, like I said, since there's no slipping at the bottom, you can take the torque about A. That saves you a lot of time. So if you take torque about A, F ka torque 0, N ka torque 0, mg ka torque 0, T into 2R must be IA about alpha. I about A, parallaxes theorem, mr square by 2 plus mr square, 3mr square by 2. So T is equal to 3ma by 4. A is equal to R alpha. For the block, mg minus T is equal to m into A block. T will be 3ma by 4. And the block acceleration is 2A. That will be 4 to 8, 8 plus 3, 11 ma by 4. So acceleration of the cylinder, this A is the acceleration of the cylinder, which is 4g by 11. Acceleration of the block will be twice of this, 8g by 11. Check. Clear with the steps? Same thing we did, right? Every time we're doing the same thing, if you see. We are drawing the FBD, then we're writing the constraint equations. Since it is on a floor, it is not slipping, you can take the torque about the bottommost point. If they ask you to find the friction, you can do that also. And you'll get T minus F is equal to ma. You'll get friction value from there. You can find everything. You can find the tension in the string. You can find friction. Have a look at the steps. Any doubts on this? Yeah. Next thing. That's a little about rotation and rolling motion. The next thing is rotational kinetic energy. So when a body is rotating, it does possess energy. So how do we calculate that? Consider a body rotating with omega. So if you consider a particle here, mi, going in a circle of radius ri, so this particle will have a speed vi, which is nothing but ri into omega. This kinetic energy of this ith particle will be half mass of the ith particle into vi square. That will be mi ri square omega square. So if you add the total kinetic energy of the system, that will be summation of kinetic energy of all these particles. You end up with again sigma mi ri square. Now remember, all will have same omega into omega square. This is what I was saying. You can see the term again keeps popping up every time that sigma mi ri square keeps popping up. That was the reason we have calculated ICA value beforehand. So kinetic energy of a pure rotation. So if a body is rotating about an axis, then this is half I about that axis omega square. Clear with this? So that sigma mi ra square ka term keeps popping up every time. So that was the reason we calculated it beforehand and kept it ready. So this is how you find energy for pure rotation. Yeah. What happens if the body is rolling? So if you take kinetic energy of a rolling body, this is V and this is omega. You can split this into pure translation and rotation about center of mass. Rolling body, or this translating and this thing is kinetic energy of translation. Kinetic energy of rotation about center of mass. This will be, you will assume all the mass is located at the center of mass, half mv square, plus stand on the center of mass, then you'll see half ICOM omega square. Where we proved this? This we proved in center of mass when we wrote that energy ka term. Remember this discussion? Kinetic energy of a system is kinetic energy of center of mass plus kinetic energy about center of mass. Kinetic energy of the system is not kinetic energy of center of mass. So there's an extra term there. So this is page 90. Center of mass may be proved this. There, that's your formula there for a rolling body. So you can split the motion into translation and you can split the motion into a rotation about center of mass. And then you can just add each component there. But still, this does not give you the complete result. Now, in chemistry, right, if you have already studied thermodynamics, did you guys hear this thing, degrees of freedom? If chemistry, if it is done, we are going to do it anyway. So the actual formula goes like this. We define something called degrees of freedom. So basically, this thing tells you the number of independent ways in which system can possess energy, or in independent ways it can have motion. Can translate or rotate. So, for example, if you take a body, right, it can go in x-axis, it can go in y-axis, it can go in z-axis. Yeah, keeping it simple. So, if you take a particle, it can have three translations: plus, The body can rotate about x-axis. The body can rotate about y-axis. The body can rotate about z-axis. So it can have three rotations. So the total kinetic energy will be half m vx square, half m vy square, half m vz square. This will be half ix moment of inertia about x omega x square, half iy omega y square, half iz omega z square. So actually three rotational components. But when you take about an axis, there will be only one omega. But if it is a point of rotation, then you can have multiple rotations also. It has three rotations and three translations. So when you take the previous example, this guy, the kinetic of a rolling body, this is one translation and one rotation. For example, if we take the Earth going around the Sun, Earth is rotating about its own axis, and the Earth itself is rotating around the Sun. That's a rotation plus a rotation. Are you clear with this? So blindly don't use this formula, kinetic energy half mv square plus half icm omega square. This formula is valid when you have one translation and one rotation. If the body does not have translation, you can't use this. So we will do a problem on this. Are you clear with this? For example, if someone asks you what is the kinetic energy of the Earth which is rotating around the Sun and with its own rotation and revolution, then you have to add two rotational kinetic energies. Clear with that? So let's see a question that will make things more clear. But everyone clear with this thing? Now, in chemistry, they have something more. If it's a triatomic molecule, there is something called vibrational degrees. Let's not get into all that stuff. Let's see. Let's say we have a rod and we have a disc. The rod ka mass is m, length is l, this is m and r, this is a disc. Just like your table fan, swinging table fan. This disc itself is rotating, let's say with omega 1, and this whole setup is going in a circle with omega 2. This is like a swinging table fan. Are you getting how it is? The disk itself is rotating, and the rotating disk itself is going in another circle. Find the kinetic energy of the system. Now, if you try to use the formula half mv com square half I cm omega square will be gone. There is no translation here. Try. I'll give you a minute or two. Let's see how you handle this. Any answers? C. So let's split this into two parts. First, let's take only the disk plus the rod in the disk. The reason you don't take the rod here is because the moment of finish of the rod passing through the axis is anyway 0. This is omega 1. This is omega 2. So this is rotation about your own axis. This is your revolution. Basically, both are rotations only. I'm just calling it revolution for an easy thing. So what is the kinetic energy for this? This will be half the moment of inertia of the disk, half I omega 1 square, which is half. What is the moment of inertia about the diameter, about the axis, mr square by 2, omega 1 square. What about this guy? Now there are two parts here. Half the moment of inertia of the rod about that axis plus moment of inertia of the disk about that axis, the green line, and omega 2 square. And now be careful here. For the disk about this axis, that's your diameter, is mr square by 4. But I don't want about that. I want about the axis. So this will be half moment of inertia of the rod is ml square by 3 plus the disk will be mr square by 4 plus parallaxis theorem ml square omega 2 square. Clear with this? Got what we did? So the kinetic energy of the system one by 4 mr square omega 1 square plus 1 by 2 4 ml square by 3 mr square by 4 omega 2 square. Check. Is that clear, everyone? So for the rod, it is the edge, and for the disk, you have to, it's a diameter plus parallaxis theorem. All clear with the steps? This is a question from Meredov actually. So we got a sphere like this. Something similar. And this whole thing is going in a circle. Able to visualize how it is? So we got a sphere here and someone drilled a rod through this. So the picture is like this. We got a solid sphere. So someone made a thin hole there and they kept a rod inside like this. And then what you started doing, you started pushing the rod. Now, because you're pushing the rod, this wheel started rotating. So this wheel also started rolling omega 2. And this whole setup started going in a circle. Making sense how it is rolling on the floor? Is the picture clear, everyone? Can you display next disk? Moment of inertia of the disk is what? About this axis, what is the moment of inertia? Right? mr square by 4, right? No, about the diameter. But you want about this axis, right? And this distance is L. So parallaxis theorem, mr square by 4 plus ml square. Sure. So let's say this is omega. Let the mass of the sphere be m, and the radius also be r, right? And let the rod be massless. Can you find the kinetic energy of this system? Omega 2 is not given, only omega is given. So you have to find omega 2 also from omega. There is no slipping.
Sir, can you explain the question again, please? Like what that sphere thing is?
So we got a sphere and someone drilled a hole, right? The rod is placed along the diameter. So basically a thin hole. This picture is a little messed up. That is the thing. The hole is drilled along the diameter. And a rod of length. That is our rod of length L. Let's make it this is also given as R already. ठीक है, rod of length L is inserted. Right, and the rod is rotated. So what will happen when you are trying to rotate this? Even the cylinder will start. The sphere also will start rolling, right? You're getting how will the picture look like? Meaning, if you look at my screen, it is something like this. So my hand is the sphere. So you're putting it inside, sealed, and now you're dragging it. Now, when you're dragging this, what will happen? Even the sphere will start rolling like this.
Yes, sir, I get it. Sir,
समझ में आ
also,
रहा है shape कैसा है?
what do we have to take as the radius of that circle which has been formed?
That is given as R.
Okay, because you gave the L separately. That's why I'm asking.
That is the length of the rod, ना पूरा L. So that is also R. Actually, dimensions match नहीं हो रहा है ये. This I can't take it as R. Take it as smaller. And a rod of length, a rod is inserted and rotated, which makes the sphere also roll. I know, picture can be a little confusing. Find the kinetic energy of the sphere. Take the mass of the sphere is capital M and radius is smaller. Clear what I'm asking, na? So this thing is also right. This there is no translation here. This is a rotation plus a rotation. How do you know it is not translating and rotating? Do you guys remember the definition? What is translation? What is rotation? So ask yourself. Suppose if you take a sphere, okay, let's say it's not rolling. Forget about rolling. If you just take the sphere and make it go in a circle. Now you tell me, is every point on the sphere covering same distance or covering same angle? They're covering same angles, right? Then what kind of motion is this? Rotation or translation? It's a rotation. Do you remember? In a translation motion, every point will cover equal parallel paths. Are you clear? How do you know it is not a translation and it is a rotation? So first you need to find the sphere ka omega also. And it is not slipping on the floor. So this center of mass, the center of the circle, whatever, will be going in a circle with what speed? So velocity of the center will be r into omega. Okay? And let's say this sphere itself is rolling with a speed omega dash. Now for the sphere, the center is going with Vc, and this guy is rotating with omega dash. That means at the bottommost point, you'll have Vc, and this will be small r omega dash. Since this is placed on the ground, it is not slipping. Velocity of the center must be equal to r omega dash. And velocity of the center is r omega, which is equal to r omega dash. So omega dash is capital R omega by small r. This is the relation between both the omegas. Are you clear? So if you try to rotate that big sphere with omega, then the sphere will start rolling with omega dash. Got it? That's the first thing you need to find. They didn't give you both the omega. Any doubts on this part? This point is exactly below this, so it's not slipping. And then you're done. So you can split this motion into two parts. One, your self rotation, omega dash, plus you can treat the sphere like just a solid bob, and it is rotating about this axis with omega. This will be moment of inertia for a solid sphere is 2 by 5 m r square, small r square, omega dash square, plus what about this one? Moment of inertia about the center will be 2 by 5 m small r. This distance is capital R, so you have to use parallaxes theorem. This will be half 2 by 5 m r square plus m capital R square into omega square. That's the kinetic energy of that revolution. Is that clear, everyone? Most common mistake people try to use that half mv com square plus half I co omega square. Remember, that's only for translation plus rotation. Any doubts on this? So this is a rotation plus rotation. Clear with these problems? So this one and the previous one kind of same, but in this case, there is also, you have to find the relation between the omegas. So that was the additional thing. Got this? So now, other than that one concept, right, everything else is same. You have your regular work per energy. The only difference this time, you'll also include rotational kinetic energy when you're solving. So let's go ahead with a few more. But any doubts on this, please ask. How did you get omega dash and the two parts? Anything you're not clear, please ask. Clear na, Advai? Yashvi? Trishi? Okay. So let's say we have a bowl shape here. This side is rough. There is no slipping. This side is smooth. Here you took a solid sphere. Mass m, radius r, and you released it from height h. A is the bottommost point. First question. Find the speed of the ball when it reaches the point A. Find the maximum height it will go on a smooth surface. initially released from rest. And there's no slipping. So as the ball is rolling down, it will start rolling. So find the speed when it reaches A, and after that it enters the smooth side. So what is the maximum height it will reach on the smooth surface? Again, remember the steps of work per energy. Same thing. Step one, choose your system, define your initial state and the final state. Define your reference line for potential energy, right? Potential energy, kinetic energy, spring energy. If work done by external force is zero, conserve energy. So that entire story is same. The only difference this time when you write kinetic energy, you'll write half mv square plus half I omega square. Think, take a minute, then I'll show you the first part. Let's see. Step one, choose a system, Boltzmann system. Step two, define your initial and final state. So I want to find the velocity at A. This is state one, this is state two. Next step, draw the final picture. So when it reaches here, let the speed be v and let it be omega. Since it is not slipping and it is a ground, v minus r omega must be equal to v ground, which is zero. So v is equal to r omega. Next thing, define your, so loss in potential energy is gain in kinetic energy. Energy in state one is equal to energy in state two. So initial potential energy mgr, mgh. Final energy, potential energy is zero, which is half mv square. Now see, this is translating and rotating. So it's a rolling sphere. Half I center of mass omega square. mgh, half mv square. Moment of inertia of a solid sphere, 2 by 5 mr square. So that's what I'm saying. If you don't know the results, you're gone. But r omega is nothing but v. So 2 will go off and that will be 7 by 10 mv square. V is equal to root over 10 gh by 7. That's it. This is a mains level equation. Right, Arya? Is the first part clear, Arya? The second part of the equation. Now, after crossing A, when it tries to go up, then what happens? Now, what is the catch? This is a good one. Listen. So, before even solving now, let's ask yourself what is exactly happening here. So, on the left hand side, when you're coming down, if you draw the FBD of the sphere, these will be the forces. So, there is a friction here, F, N, and there is an mg here. So, there is an alpha here. So, if you take torque about center of mass, F into R is I center of mass into alpha. So basically, this alpha is creating that omega. You're getting it? So the body is able to roll. But once you enter the other side, see what happens. Once you enter this side, mg, normal reaction, and friction is 0, if we take torque about center of mass, we get 0. Therefore, alpha is 0. Therefore, omega does not change. Means if you take a sphere and if you spin it and if you keep it on a smooth surface, it will just be there spinning forever without moving anywhere. Is that making sense? So if you take a ball, rotate with omega and put it on a smooth floor, the ball will just stay there and will just keep rotating forever. It will not go left, right, it will not go anywhere because there is no friction, nothing to stop. So that means on the right hand side, once it enters the smooth surface, the ball omega doesn't change. Speed can change because of mg sine theta. So omega of the ball does not change once it enters the smooth surface. So now again, if you draw the FBD there, so this was the rough side. So initially ball was here, then the ball came here. This was V. This was omega. And finally the ball will reach somewhere here. Now when the ball reaches here, it will come to rest, but omega will not change. Omega will still be same. This is your state 3 and this is your state 2. This will be the new height h dash. Is that making sense? So as the ball is going up, speed will keep decreasing because of mg sine theta, but omega will not change. So at the highest point when it reaches, the ball is still spinning there and then comes down. So now if you conserve energy between state 2 and state 3, you can actually clearly see and tell only the translation energy, half mv square plus half I omega square. Only the translation energy becomes potential energy. This will be mg h dash plus half I omega square. What is v square? 10gh by 7. H dash is 5h by 7. Clear with this? Clear how we approach this? That so you have to be careful with that omega also, no? All clear. Let's see one more. Any doubts on this? Anyone not convinced with anything here? So basically on a rough surface, the friction is actually stealing energy from the translation and giving it to rotation. It's making it rotate. The friction is the responsible for the ball to roll. If there is no friction, the ball won't roll only. Let's
So,
see.
so
Yeah.
if there is no friction, the ball will be more fast than it
Yeah.
should be, right?
Because you are giving all the energy to translation instead of rotation. So you'll go fast now. So height h, theta. This is no slipping. So when I say no slipping, there is friction. We have a hollow shell. Hope you remember the moon definition of hollow shell. Mass and radius r. Right? Now this thing is filled with water. Non-viscous water, meaning there is no friction. Mass, small m. Case 1, it is in liquid state. Case 2, the liquid is frozen to solid. Find the speed when it reaches the ground in both the cases. Is the question clear? We have a hollow shell. You filled it with some liquid. Case one, the liquid is non-viscous, so there's no friction, nothing. Case two, you cool down the liquid and it became ice. It became like a solid ice and it got stuck to the shell. Now, in both the cases, when you release it from the top, it will come down rolling. Find the speed when it reaches the ground. How do we approach this? Think it's a good one. What difference does it make if you have a liquid and if it becomes an ice ball? Let's see. What is the catch? Look at case one. So inside it is a non-viscous liquid, meaning so this is the liquid. So let's say if I take 3 points inside the liquid A, B, and C. Okay. And let's take 1 point on the shell, D. Now, as this thing comes rolling down after some time, the liquid will not rotate. There is no friction, right? So these points A, B, and C will still be same. If you see, they will just go in a straight line. Whereas this point D must have come somewhere here. You're getting what is happening? The shell is rotating and rolling, but the inside of the liquid is simply going in a straight line. Because there is no friction, liquid does not rotate. Since there is no friction, that is the meaning of non-viscous liquid. The water does not rotate inside. For liquids and gases, we call it as viscosity, and for solids, it's called friction. Clear with this? So there is no rotation there. So then you're done. Loss in potential energy is equal to gain in kinetic energy. Be careful. Don't treat the spherical mass as m plus m. You have to treat the shell differently and the liquid differently. So loss in potential energy will be m plus m gh. The total mass, you lost this much potential energy, is equal to half small m v square. This is the kinetic energy of the liquid. Only translation. Because the liquid does not rotate. plus half capital M V square plus half moment of inertia of the shell, which is 2 by 3 mr square omega square. This is for the shell. And it's not slipping, so V is equal to R omega. Solve this, you'll get the answer from there. Are you clear with this? What will be different if it becomes an ice ball and if it gets stuck to the shell? If it is frozen and it will get stuck to the shell, this time, this A, B, C, D, this is B, this is A, and this is C. You're getting this line became like this. So even the ball is rotating now. Now, because it got stuck to the shell, it will roll with the ball. So the story will still be the same, but extra will get one more term now here. We will get half mv square plus half the moment of inertia of a solid sphere 2 by 5 small m r square omega square. This is for that ice ball. Got the difference? So in the second case, you get that extra rotational term. In the first case, there'll be no extra rotational term because it's only translating. The liquid never rotates. Clear with this? Yeah, that's how can they play with that rotation and everything. See, here we even know what is Brownian motion. So let's not worry about it right now. All clear with this?
So technically speaking, that it's not possible, right? Same water, same
What?
mass, same volume for ice
Which
and water.
one?
Like for ice
Why?
and water in to exist in the same volume.
So fine. No, the shell will not let it expand. Kya problem tha? The shell will be under pressure.
So where the shell will break, right? It's
The
not
shell is very
possible.
strong.
Okay.
Shell is very strong. It is a strong shell. All clear with this? Brownian motion is based on temperature. So don't worry about that right now. We'll see in the thermodynamics. Clear with this question? If you look at this question, right, not tough, right? But you have to think a bit. And this is the reason if you see in Centromos, we spent time in the beginning to define what is translation, what is rotation. So if you don't have a clarity what is translation rotation, these problems you will have an issue there. Clear with this? So let's say we have a rod. This is a hinge. Mass and length L released from horizontal position. So then the rod will start swinging because of gravity. So let the rod rotate by theta. So at this point, it will gain some angular velocity. Find omega and the hinge reaction when the rod rotates by theta. Just omega is a mains question. If I ask you hinge reaction, it becomes an advanced one. Let's get this. Let's get omega. That you can start. Mm, let's see the omega part. Same story. Step one, choose your system, Rhodesian system. Define your initial and final state, conserve energy. This is my initial state. This is my final state. Where is the center of mass? Center of mass is here. Now finally, center of mass is here. So this distance is L by 2. So this height will be L by 2 sine theta. So the center of mass has fallen, a height of L by 2 sine theta. Loss in potential energy is equal to gain in kinetic energy. Remember, the rod is doing pure rotation about the hinge. So loss in potential energy mg L by 2 sine theta. Since this is pure rotation, half I hinge omega square. Right? If you have a fixed point and if it is rotating about that, keep your life simple. Like just take about that. This would be mgl sine theta, 2 goes off. And I about the hinge will be ml square by 3 omega square. Omega will be root over 3g by L, 3g sine theta by L. Check. If it becomes vertical, theta is 90, then omega will be root 3g by L. Now, how do you find the hinge reaction at this instant? Let's get that. Let's see. What you want to find hinge reaction, then what to do? Draw the free body diagram. Now, how to take hinge reaction? Remember, I told you hinge reaction you can take in any two perpendicular directions. So for convenience, I will take this as nx. I will take this as ny. You just have to be perpendicular. It doesn't matter which direction though. You can take vertical, horizontal, and x. That is also fine. This is mg, but you will see why I took this way. And you are going in a circle. Since you are going in a circle, there will be centrifugal force m omega square L by 2. Right? Any other force? That's it. These are the three things there, and then you can divide this mg also into components. And not only that, there is also an alpha here. So center of mass there. Actually, if you don't want centrifugal force, let's do the other way better. Let me use accelerations only. I can take centrifugal force, that is also fine, but okay, first let me resolve the components. The centrifugal force. And what is this mg ka components? This is theta. This is 90 minus theta. Nx, ny. This would be mg sine 90 minus theta, mg cos theta, mg sine theta, centrifugal force m omega square L by 2. These are all the things in this direction. And your center of mass is going in a circle. So this will be acceleration of center of mass, which is L alpha by 2. So I need to find alpha. So find torque about the hinge. The only guy who's creating torque is mg cos theta. L by 2 is equal to I about hinge into alpha. Alpha will be 3g by 2L cos theta. That's your alpha. So then you're done. You can write the equations. Nx must be equal to mg sine theta plus centrifugal force, or else you would have taken centripetal acceleration also. Same thing you would have got. M omega square L by 2. And what is omega? Omega is 3g sine theta by L. So if you substitute there, that will be 3 by 2 sine theta plus 1. This will be 5 mg sine theta by 2. And what about ny? Mg cos theta minus ny is equal to mass into acceleration of center of mass. So ny will be mg cos theta minus a center of mass will be L alpha by 2. That will be 3g cos theta by 4. There. Now, why did it take nx ny like this, and why didn't it take it vertical? If I have taken ny and nx and mg, the problem would be, since this guy is going like this, a centromass will go like this. I have to divide centromass acceleration in the components, right? Centrifugal force into components, or I have to divide nx and ny into components. So it actually becomes too many components. That's it. That is the only reason. So there is nothing more. You could have taken that. You would have still got the same answer. So what is the hinge reaction? Nx square plus ny square. Remember, if you take like that, your nx and my nx will be different. But when you square them and add them, you'll get the same answer. Are you clear with the steps? You got a lot of things here. Circular motion, rotational mechanics, conservation of energy. Any doubts on the steps? Clear with this? Check it out. Take a break. Come back by 9:45. We'll continue from here. Any doubts so far? Come back by 9:45. Chalo, Tata. Remember this question? We have done this in momentum. This is smooth. This mass is 2m. We have a solid sphere, mass m, small r. This is a quarter circular track, radius r. This is point A, and there's no slipping between them. Matlab there is a friction on the wedge. Find the speed of the ball when it reaches point A. Other scans on. Let's get this. Do you guys remember this question? Then this is the first time I explained. This is the same thing if you observe. Say. But here all surfaces were smooth. The ball was not rolling. It was simply sliding. Now it will roll. This is a better one. Let's see how you handle this. Try. I'll give 3 minutes.
So can we consider R very well less than the great R?
No, don't consider. Don't consider. You will need that smaller. Hmm. How do you handle this? What is the process? Step one, choose your system, draw the final picture. Wedge in the ball is a system, draw the final picture. Assign velocities, find the no slipping condition, and then conserve energy. Let's see. So when the ball reaches here, let this speed be v1, let this go with omega, and let this guy go with v2. Since there are no horizontal forces, linear momentum is conserved. Initial momentum is 0. M V1 minus 2M V2. V1 is equal to 2V2. Next thing, initial energy is equal to loss in potential energy is equal to gain in kinetic energy. So initially, if you see, the ball is at a height of r from the surface. This is also r from the surface. So the difference is still capital R only. Mg r is equal to half m v1 square plus half I center of mass omega square. This is for the ball. Half 2m v2 square for the wedge. Till here, most people get it right. Then normally people do a goof up. Then they think v is equal to r omega. That's the goof up. Now, if you look at the sphere here, and if you look at the surface, this guy is going with v1 and this guy is rotating with omega. So this point is going with v1 minus r omega. And this point is going with v2 backward. Let me write it like this. So let's say this point is going back with r omega minus v1. So the no slipping condition is r omega minus v1 is equal to v2. Are you clear with this? That's your no slipping condition. It's not v is equal to r omega. Are you getting why every time I keep saying don't say v is equal to r omega? You will get trapped like this. V is equal to r omega is never the no slipping condition. It becomes no slipping condition in some special cases when the floor is not moving. Here the floor is moving. And we know V1 is nothing but 2V2. This will become 2V2, that's 3V2. There. So V2 is equal to r omega by 3. Or you can substitute V1 also. So V1 will be 2r omega by 3. That's your no slipping condition. Clear with this? Now you got everything. So just substitute there and solve, you'll get the answer. This is your equation 3. Any doubts on this? Clear, na, Samyak? Ishman? Aditi? Obia? Clear? Pratyasha? Clear ना हो गया? Confused? बोलो ना. Clear? Anvita? Shreyansh? Utsa? Tanishka? Clear? So want to solve? We can solve this. MGR half MBN square half solid sphere 2 by 5 M small r square omega square plus half 2M V2 square. This will be 1 by 5 M r omega. Now be careful. R omega is 3V1 by 2. And V2 is nothing but V1 by 2. There, you got everything solved. You'll get V1 from here. Clear? I don't think you'll get any good number though. Clear the equations. Yes, we have done this in momentum. Let's see one more which you have done before, but a little variation. Any doubts on this thing? Any step you're not clear here? So there are 3 steps. Linear momentum, energy conservation, no slipping condition. Okay. Let's see the next one. I hope you remember this. Work per energy, vertical circular motion. So we got a track here. We got a solid sphere. Mass m, radius r. So this is a track of radius capital R. So from this, the base till here, this height is h. Not from the center. Huh? The A is the topmost point. So the first question, find H minimum to reach point A, basically to complete the vertical circle. Right? If H is equal to H minimum, find acceleration of point B. The B is a really good one. This would be a pretty good advanced paragraph question. Acceleration of point B, right? Which is when sphere reaches the horizontal position. So this position. So when the sphere reaches the horizontal position, that B is the topmost point of the circumference on the sphere. Not on the track. So on this sphere ka circumference, there is a point B here. I want that point ka acceleration. Topmost point on circumference of the sphere. Are you getting what I'm asking? First, let's get the first thing. Then we will see the second part.
Sir, no slipping.
No slip. Hmm.
Sir, also is the track fixed?
Track is fixed only, Nari. God, don't just poke everything, solve. Then उसके बाद पूछोगे ग्रेविटी है पूछ लेना उसके बाद एंड देन से ना इज दैट अ लून इज फुल मून डे और नॉर्मल डे बिकॉज मून का अट्रैक्शन भी आएगा और क्या चाहिए बताओ सॉल्व ना
टेक्निकली वो रहता ही है, दिखता नहीं है.
चलो करो नहीं रे 2 बार नहीं होगा यू इग्नोर द रोलिंग कंप्लीटली वाइल्ड गेस किया यू ना आई शुड पंच यू द नॉर्मली ओनली द आंसर इज 5r/2 now you are rolling so it should be definitely more than that thing right 2.5r. You guys remember the vertical circular motion? What is the catch? At the highest point, you can't have a zero speed. Remember? That was the main theme. Okay, now it is 10 o'clock. Now this is time when people will start leaving for some reason suddenly. People vanish now. Don't worry, I took the photograph when you guys came, so I will know who left right now. Vanishing time has started. क्या होता है मतलब after 10 o'clock moon comes out and you become a werewolf or something, so you don't want us to see and you just close the cam and then you start howling, oh, types, something of that sort. Could be. That would be pretty interesting though. Then you should definitely go to IIT. You have a big forest. After night 10, you can start roaming in that forest. Uh, yeah, that would help.
Sir, अब तो at least let us consider R is small than R.
You and your R is small. नहीं रे, R is not small. If R is small, you won't get the second part का answer. Why are you obsessed making that small R का thing negligible?
So
You and your lazy fellow to calculate.
at least for
Don't
writing the
write it.
gravitational potential energy.
कुछ नहीं. सुनो. So we will talk about that B later on. So let's see this guy. So when this sphere reaches the topmost point, what are the forces? mg, the centrifugal force. What is the centrifugal force? Anyone? M v square by r minus r. Remember? Be careful. The center of mass is not going in a circle of r. It is going in a circle of radius r minus r. You have to take the center of the sphere. So at the highest point, n must be greater than equal to 0. You don't want to lose contact. So mv square by r must be greater than equal to mg. So therefore, v must be greater than equal to root over r minus rg. So the minimum speed at the highest point is root r minus rg. So as long as you have at least this much speed, you will not fall down from the topmost point. Clear? This is the speed at the topmost point. Next thing, state 1, state 2. I will take the ground as the reference line. Energy in state 1 is equal to energy in state 2. Initial potential energy, mg h plus small r. Because remember, I took h from the bottom, so plus small r you have to add. This will be the potential energy mg. What will be this thing? 2r minus small r. Are you getting? You have to take the center of mass, no? This will be r minus r, and this will be capital R. So it is 2r minus small r. Are you clear? It's not a point particle anymore. You have to take the center of the sphere for everything. Plus half mv square. And since it is also rolling, half I omega square. Please check the equations. नहीं आ रहा 17 नहीं आएगा. That also will be 27. I give you decent numbers. Are you clear with the steps? Then you just bring it everything and solve here. So if you bring that smaller that side, this will be mgh. If r goes that side, this will be mg, 2mg, r minus small r, half mv square. I'll write it in the next page. Half I omega square, this will be 2 by 5. mr square omega square, and it is not slipping. So, and the ground is at rest, so v is equal to r omega. That will be 7 by 10 mv square. But what is v square? R minus rg. Mg goes off, we get h is equal to 27 r minus r by 10. This is your h minimum. Yeah.
Sir, how did you write a 2 mg into R minus R?
Yeah, take this R and shift it that side, na record.
Sure.
Are.
Then why didn't you write 2r minus like 2 capital R minus 2 small r in the
नहीं स्मॉलर क्यों आएगा देखो ना ये सर्कल था ना
but the center
ये
of mass
ये डिस्टेंस कितना था स्मॉलर
uh,
ये डिस्टेंस कितना था बताओ
but since the center of mass has traveled 2 into
मैं
r
आई टू
minus
मैं ग्राउंड रेफरेंस इन ग्राउंड लिया मैंने ना
सर आई मिसरेड द इनिशियल थिंग. वो हाइट आपने बॉटम से दिया है एच.
मैं क्लियरली लिखा था एच वाई पे बॉटम करके यू आर द वन हु इज डांसिंग अराउंड स्मॉलर को इग्नोर करो करके चेक आउट द स्टेप्स आर यू क्लियर विद द स्टेप्स clear what we did if you think about this we didn't do anything different than what we did in vertical circular motion. At the highest point, it can't fall down. So centrifugal force must be greater than equal to mg. We have found the velocity. Then we conserve energy from initial to the final state. The only difference here, the r phi omega square is an additional term. Are you clear with this? This is still a decent question. This won't be the actual advanced question though. If it's an advanced paragraph, this will be the first part. The second question is the actual thing. Let's get this. Now, when you're releasing the ball from h minimum, when it reaches the horizontal position, so remember this ball is spinning and going up. So when the ball reaches the horizontal position, B is the topmost point on the sphere. I want that point of acceleration. Let's see. It's a pretty good one. How do we do this? Let's start with this thing. Can you find the speed when it reaches point B? Let's start with that. Let's find the speed of the ball when it reaches point B. Just to give you an idea, you know how many acceleration that B will have? 4. I mean, not exactly 4 directions, but there are 4 components. Let's start with that. Let me get all the data, then I'll show you. So this is your H minimum. So I know that. This is state 1. So the speed is here. This is R. This ball will have a speed V and will also rotate with omega. So initial energy mg h plus r. This will be mgr. half mv square. Plus half I omega square, which is 2 by 5 mr square omega square. And it's not slipping on the float, so v is equal to r omega. So from here you'll get v and you'll get omega. It's okay, leave it there. So you got v and omega. This is fine. I can put the values and get v and omega from here. Then there's something more. I'll just exaggerate this. At this point, when you draw the sphere, if you draw the forces, there is a friction acting upward. Remember, it is not slipping, so there's a friction. There's an mg, and there is a normal reaction. So this guy will have alpha, and it will also have an acceleration. Basically, it is decelerating. Both the speed and omega both are decreasing as it goes up. Then, our favorite point A here. Let's not call it A because A already took. Let's call it some P. If you take torque about P, then there's only mg ka torque, which is mg into r, is equal to I about the point P into alpha. We get mgr, I about P solid sphere, so 7 by 5 mr square alpha. Alpha will be 5g by 7r. So the acceleration will be 5g by 7. So at that instant, the sphere is decelerating down with A and it is also rotating with alpha. Clear with everything? So all this data is clear. So we got V, omega, we got A, alpha. So at that instant, I found the velocity, omega, acceleration, and angular acceleration. Now look at this. Now what are you asking? You want to find the velocity of point B. So there are two things happening here. This sphere ka center is going in a circle, right? So this will experience a centripetal acceleration towards the center. This will also experience an acceleration which is atangential downward. So this A centripetal will be velocity of the center square by r minus r minus I cap. This is your A centripetal. And A tangential, just now we derived 5g by 7 j cap. This is the acceleration of the center of the thing. So acceleration of the center of the sphere. Remember that point itself is going in a circle. Is minus v square by r minus r I cap minus 5g by 7 j cap. Great. Now go and stand on the center. If you go and stand on the center, you will think this guy is going with alpha, right? And remember, this is also rotating with omega. So this point B here will have another centripetal acceleration, which is omega square small r, and you have another tangential acceleration, which is small r alpha. Isn't it? If you go and stand on the center of the sphere, don't you think B itself is going in a circle? So acceleration of point B with respect to the center will be minus small r alpha I cap minus omega square small r j cap. So acceleration of point B with respect to the ground frame will be acceleration of point B with respect to the center of the sphere, but your center itself is going in another circle. That is the center with respect to the ground. Are you clear? Why you got 4 terms? Are you getting the steps? Your center itself is going in a circle. So that is going in a non-uniform circular motion. So it will have A centripetal, A tangential. And when you stand on the center, B itself is going in another non-uniform circular motion. That will have A tangential, A centripetal. Add them all. That will be the final answer. Are you clear with the steps? Got this? It's a pretty good one. You should definitely try it again on your own. Right? I can take different points actually. You can make it more messy. You can take a when the sphere is here, when it is making 60 degrees, and you can say the B is somewhere here. Still, there will be four parts. You have to take components and solve it. But there, this is a circular motion. Remember that I told you, Magica में cup and saucer ride, kind of like that. It's a rotation under rotation. All clear with this? Yeah.
Sir, can you like please numerically verify my answer?
I can't try. Check it out. You should get the same equations. I'm more lazy than you to solve. अभी B and omega कौन निकालेगा? Figure it out. If you got the equations, then you are done.
सर
But
कुछ
you
तो
got the same
17
equations,
वगैरह
right?
है, हाँ कुछ तो
आ
17 वगैरह
सकता है.
है.
वो तो आएगा ऐसा कुछ. Numbers won't be great. People are exhausted already. Let's see. Last one for the day. We'll do an easy one only. We have a carpet. This is a tightly wound carpet. We did something like this in foundation. Carpet ka radius is R, mass M. So there is no space between them. Huh? I didn't draw it properly. And then what happened? This carpet started rolling on the floor. There is no slipping. So as the carpet started rolling on the floor, you know what will happen. The radius becomes smaller. The radius becomes R by 2. Find the speed of the carpet when the radius becomes R by 2. In case you're wondering, the picture will kind of look like this. Uh, something like this. You have a carpet there and it's just rolling on the floor. So initially carpet is at rest and you give a slight push and the carpet started rolling on its own. Find the speed of the carpet when the radius becomes R by 2.
सर कुछ इनिशियल स्पीड वगैरह नहीं है क्या?
You just pushed it, so push नहीं. It starts moving on its own. Again, remember the process. Step one, choose your system. Final thing, same thing. Story doesn't change. Yeah, it looks a little different though. So this is your state one. This is your state two. Where is the center of mass initially? This is the center of mass at a height of r. Now where is the center of mass? R by 2. Now the important thing is this. Is the mass still same? Here the mass m is density into volume, right? Pi r square into L. So here the mass m will be density. This become pi r by 2 whole square into L. So this is actually m by 4. So this carpet ka radius becomes m by 4 and radius r by 2. Are you clear? So as the carpet is rolling the floor, mass keeps changing. Got this? So energy in state 1 is equal to energy in state 2. And at this instant, this carpet is also moving with speed v and is also rolling with omega. And v is equal to r omega because it is on the ground. So initial energy, mg/r, potential energy. Final potential energy, m by 4, g r by 2. This is your final potential energy. Mass gets messed up. Plus half mv square. But what is m? M by 4. Plus half I omega square. But what is I? mr square by 2. It's a solid cylinder. M by 4. R by 2 whole square by 2. This is the moment of inertia of the cylinder. Are you clear with the steps? So the main idea is that the mass is messing up. You can simplify this now. This will be mgr. mgr by 8. mv square by 8 plus how much is this? V is equal to r omega. That's mv square. 4, 4, 16, 464. That would be 7 mgr by 8 and 1 by 8 multiply 8. 9 by 64, 8. Ha, I messed up. V is r by 2 omega. Remember, radius changed. So this is wrong. That would be 1 by 4 m by 4 r square by 4 omega square. But r omega is 2v, so 2 goes off. So we get mv square by 16. Then 7 by 8 gr, and that's 3 by 16, 8, 2, 14 by 3. Check. That's your answer. Clear with this? Again, if you actually understand the mass is becoming 1/4, it is easy to solve. बोलो नाले.
Sir, can we apply conservation of angular momentum?
You can't. Why?
So I guess there is
Tell
like
me.
net torque or something.
तो वही तो है ना. Figure out. Tell me what is that. देखते हैं. We will see that in rotation. But you tell me why it is can't.
Also, sir, like I have one more doubt. Ki is the mass which is leaving generating a kind of thrust force?
No, we are ignoring that. मतलब see ना, when it just falls on the ground, it just stops momentarily. Done.
So मतलब वो ऐसा kind of thrust force की तरह act कर रहा है क्या? जैसे रॉकेट में
नहीं ना.
करता था.
No, it is not like that. Basically, see, every time it falls, it just stops. Na. Think of like this. When you're leaving this thing, what is V relative? Zero, na?
Yeah.
That way. So every time it just falls, it just stops. So that energy is lost. So we can't do anything about it. So you're assuming it is not slipping. So, and actually, ऐसा सोचो ना, what is the velocity of this point? This is already zero, right? So whichever is touching it is just laying down there. So there's no relative velocity. Slipping भी नहीं हो रहा है. So there's actually no loss of energy. Clear?
सर
Because the
बट वी
bottommost
आर
point is already at rest.
सर बट उसका रिलेटिव वेलोसिटी तो होगा ना कारपेट के रिस्पेक्ट में.
नहीं है ना. नहीं, see, look at this thing I'm saying. This is the carpet. So when it goes front, this part is already at rest. So this part is just falling there, and this is coming to rest, and it's just rolling.
Okay.
We are assuming that it's a very thin carpet. Matlab, if it is thick, na, then when it falls, actually there is some kind of a collision with the floor. We are ignoring all that.
Okay, sir.
So very thin carpet, it is just laying down. That's a good one. So next class, when we catch up, we'll continue from here. We will do few more problems on this, and we are going to study an important concept called IAR, instantaneous axis of rotation. Right, and after that, maybe we'll start off with the introduction of angular momentum also. That would be the most important thing. Okay, with that, we'll wrap up for the day. We have done almost 55 questions, so please make sure to resolve them. And remember, there's a test online till tomorrow night, so make sure to give it. So, any doubts, anything else? So, please stay back and ask, or else you're free to leave. I'll see you on Friday, same time. So, take care. Not Friday. What is today, actually? It is already Thursday, so Tuesday. So, we'll catch up again. So, those are doubts can stay back, others are free to leave. Bolo na.